Hello and welcome back to day 13. This is probably the hardest part, day 13 part 2 I should say. This is the hardest part for all the days so far, at least in my opinion. Certainly the one that I struggled the most with. When it came out, I actually had to do a lot of research around, okay, how exactly do I have to solve this problem in order for it to work in a time efficient manner. We're going to go through two ways to do this. First, the brute force calculation way, which takes forever, just so you know. Do not actually do that. It will literally take forever to finish. And then the second way will be the correct way, which we will be using the Chinese remainder theorem for that particular solution. So with that, let's jump in and let's take a look here. So what we've got here is we've got a problem for the same input that we have. We're actually no longer using the first line of the input. It's not relevant to the problem. So the second line is the only important thing. And suppose that we have the same list of IDs as above, which is what our example was, and we will continue to use that. So let's jump over to our input really quickly. Okay, well, we will copy this to be the second line of the input here. There we go. And then we'll test this off of that second line of the input. This will take some explaining. So an X in the schedule means there are no constraints on what bus IDs must depart at that particular time. So it's like you're guaranteed that a bus will be at that particular constraint. In this example, we have 7, we have 13, then we have 2 X's, and then we have a 59, an X, and then a 31, and then 19. And basically, X means there are no constraints, so we don't have to solve for those particular ones, but the requirement is that every single bus has to be staggered. So the X's, so 7, for example, the result here is 101 million, 1 million and change, and we have 1 million and change is divisible by 7, and then the next one is divisible by 13. We skip the 2 X's, right, from our input, and so we have another offset of roughly 2 here before bus 59 comes around, and bus 59 needs to be divisible by this number plus its index, right? Plus its index at that particular spot, and then bus 31 needs to be divisible by that blank plus the next index, and then 19 will come after 31. So we're calculating at what point does every bus progressively complete, and the X's will guarantee complete, but we have to calculate it for the other numbers as well. So not a trivial task to complete here, but like I said, we're going to be using the Chinese remainder theorem. I will include a link to a Wikipedia article on the Chinese remainder theorem below the video. Check that out if you want to do some fun reading, or if you suffer from insomnia, that should help. Otherwise, let's dive into the actual code. This is not a this was fun. So what we're going to do here is we're going to split up our buses. So we actually have our buses here, but I'm gonna create a new buses variable here, and this is going to be data 1, because we're going to do a little bit of pre-processing of buses here. We're going to say that buses is going to be int bus minus the index, as well as the int bus for index bus in enumerate buses dot split along the commas. We also need to assume that bus does not equal X, right? Because those are our inputs. Okay, so what did I do wrong here? This should be it. tuple. Okay, perfect. Okay, so basically what I've done here is we've calculated the required remainder that we will have here, is that we will have the bus minus our index for index in bus, and that's the key, is that we want remainder for each of the buses. Okay, and then we'll pass buses into part 2. And these are essentially pairs, right? We have the remainder, and then we have the bus value right there. Okay, so let's actually use buses here, and we're going to be iterating through our buses. But first, what we need to do is we actually need to let's import numpy as np, because we're not using Python 3.8, and so we need to use the prod from NumPy, because 3.75 does not have math.prod yet. Okay, so n is going to be int. We're converting to integers of the numpy.prod of bus for remainder bus in pairs in our buses. Okay. Oh, I did say numpy np. There we go. Okay, so this is essentially our max value, our max value that the number probably will be, right? Is a multiple. It will probably be some number that is lower than the multiple of every single one of those numbers together, right? That would be the at the maximum what we would anticipate this number to be. And we can also use this to get a common base for each of our times. So we're going to have a total here, which is going to be 0, and we're going to go through for remainder bus in buses. We're going to say that we're going to create a base for that particular bus, which is going to be n divided by bus, right? And this is a floor division, so that we get a proper integer floor division. We're going to say that our total is going to be plus equal to the remainder, and then we multiply the remainder by the base, and then we take something that is called the modular inverse here, which is the power, or just pow actually, of base to the bus minus 2. Okay, and then we actually need to modulo this by bus. Okay, then we take the modulo of that again, but using the maximum value. That way, in case we go over the maximum value, we modulo that back down, and we are within the bound again. So total will be the modulo equals of n, and then we can return the total. Okay. There we go. Okay, so let's test this out. Three. So this is 1 million and change. Let's double check this against the actual result. Yes, that's the correct result. So we'll go back in and we will input our answers into our actual input into the input.txt, and we'll run this. So this is the correct answer right there, or it should be. Let's double check it. There we go. Yes, that is the correct answer. So there we go. Now let's go back to day 13 here, and there we go, day 13, and let's take a look at what this could potentially look like from a brute force standpoint. We'll just call this a fun way of doing this, not necessarily the best way to actually go about doing this at this point. So we're going to say, we're going to have two different functions here. We're going to say that we're going to get base time. And this is going to be our first value. And we know that the input is going to be greater than this number, which is quite large. So that's going to be that number. And we'll say while x modulo first val does not equal 0, we're going to say x plus equals 1, and then we'll return x. So this is going to be, so our very first value that needs to be divided evenly, we will know that this will be the first value that we should start testing, will be this x value right there. Okay. So now we've actually got our fun function, def, and we're going to say fun brute force pairs buses, right? Oh, there we go. Delete that. There we go. So we're going to say that our multiplier is going to be the buses and the very first value and the ID of the bus. That's our multiplier. Our time to start is going to be the get base time for our multiplier. And then we say missing is false, and while not missing, we're going to say time plus equals our multiplier. So we're going to skip by the number of buses that are here. And we're going to, oh, we do need to create an is valid, def is valid function for this particular input, right? We've got our our time remainder bus here. So we're going to say time remainder bus equals TRB. And there's a reason that we're exploding this, and I'll show you what that is in a moment. And we were going to say return time plus remainder modulo bus equals 0. Okay, so that's our is valid function. And we're going to use that down here after this time section. We're going to, we now have our new time, and we now have our remainder, right? That's from the buses, and we've got our actual bus as well. So time remainder bus. And so we can pass all of those into missing, which is going to be all of map valid, is valid. And we're mapping in the values time remainder bus for a remainder bus in buses. Just like that. So theoretically, this would in fact solve correctly, but our number is so massive, I wouldn't actually want to wait for it. So let's take this, and we're going to say x equals, and let's do 0, 0, 0, 0, 0 there. So our new x, our new starting value is going to be here, and we'll test whether or not we get the correct answer from this fun brute force method. Missing, oh. So when this completes the cycle, well, once we have found everything, then it will return the proper time. So let's throw fun brute force buses. Oh, I forget that this actually needs to be slightly different. This buses part needs to be slightly different here. Okay, so this is part 2. So let's say part 2, part 1, and this is going to be part fun. So what we've got here actually is it's going to be just the index and the integer for the bus, right? This is our new remainder. So that's our positive index, whereas the other one was the negative index, or the reverse remainder, I guess you could say. So let's test this out. Actually, we'll go up. No attribute. List object has no attribute split. What did I use? Split. This is... Okay. There we go. Okay, so that did in fact work, and it executed relatively quickly. Let's add in another one right there and another one right there. There we go. Okay, so you can see it actually does take several more seconds, right, to do that, and we're only calculating a couple million values there that we're determining. As soon as we get up into the multiple trillions, that would become take way too long to actually calculate there. So there you go. If you have any questions, let me know down below the video. Hope this was interesting. Hope this was fun. Like I said, I'll include a link to the Chinese remainder theorem for more fun while you're reading at night, trying to fall asleep. That's a good way to fall asleep. And if you have any other questions, comments, concerns, throw those in the comments down below in the video. Like, subscribe, share if you feel like it. Otherwise, I'll see you in the next video, day 14.